Hello, I'm William Nagel, a PhD candidate in the Design, Automation, Robotics, and Control Lab at the University of Utah Robotics Center. This is work that I did with my advisor, Professor Leang, investigating the cascading structure of LQT control for dual-stage nanopositioning systems. Dual-stage systems consist of two actuators, a long-range actuator, or LRA, and a short-range actuator, or SRA, connected in series so that the total system output benefits from the stroke of the LRA and the speed and the precision of the SRA. A common biological example for this is the human arm, with its elbow and wrist motion, though the most common application for this concept is the hard disk drive, where a voice coil motor moves a small piezo element attached to the read-write head. These systems can be modeled through spring-mass damper combinations, although more complicated models can be used for more complex dynamic effects. Though beneficial, some challenges do arise through this actuator arrangement, through the now overactuated system dynamics, nonlinearities, and for general tracking applications where a priori knowledge of the reference isn't available. My work proposes to account for these challenges through linear quadratic tracking control. I'm interested in adjusting the structure so the actuators have separate references, where residual tracking error of the LRA is passed directly to the SRA. Models of a prototype dual-stage nanopositioner are used, where control is executed on a single lateral axis. Additional linear state observers are included to estimate states where required by the controllers. First, looking at the standard LQT structure for a DISO system. With performance index J, the optimal control law is defined by U star, along with matrix algebraic Riccati equation for P bar and a vector differential equation for G bar that needs to be solved backwards in time. A suboptimal real-time implementation can be achieved through negating that state matrix so the eigenvalues are negative, although tracking tends to lag behind the reference. I propose to separate the LQT structure between the two actuators so that there's more flexibility in their references. The performance indexes and the resulting control law solutions are the same structure as the standard LQT, but by selecting the LRA reference to be the entire trajectory and the SRA reference to be that residual tracking error, the SRA will explicitly attempt to compensate for that lagging effect that the LRA exhibits. This concept is demonstrated through simulations conducted on dynamic models of a dual-stage nanopositioner. Linear dynamics are modeled through swept sign measured frequency responses for both actuators of a single axis, and hysteretic actuators are modeled by cascading a Prandtl-Ishlinsky model with those linear dynamics. Both LQT controllers are calculated for low-order linear models of the system with similar performance index weights. Simulated results for triangle references on 3 plant models are conducted, and overall the cascading structure improves the tracking performance. The plant that matches the LQT model exhibits a drastic reduction in the RMS error with a slight increase in the maximum error. Higher-order dynamics and hysteresis increase the error percentages for both controllers, but on average, the cascading structure improves both RMS and maximum errors by about 50% from increased SRA efforts. I'd like to thank the National Science Foundation for funding this research, as well as you for listening to this talk.